So at this point in the course, we're going to switch gears and start talking about probability. And probability just refers to the likelihood of something happening, the chances that some event may occur. So to start things off, we're going to begin with some basic probability rules. So first off, just some general statements here. So as I mentioned, probability is a measure of likelihood. It's how likely is an event going to happen. Probabilities can be any value between 0 and 1. If something has a probability near 0, that means it's very unlikely to happen. If something has a probability close to 1, that means that it's very likely to happen. Furthermore, if the probability is 0, that means that it basically can't happen. And if the probability is 1, that would mean it's guaranteed to happen. And so for doing statistical inference, we're going to have to get a handle on how probability works, because kind of big picture in the course, we've talked about how to summarize and describe data in different ways. We've talked about one way to make predictions, which is to come up with an equation of a line that you can then put values into to try to predict when things would happen. To go much further in our ability to make predictions, which is called inferential statistics, we first need to wrap our heads around what probability means first. So, some terminology. An experiment, this is some sort of activity that you're going to do. It's an action, a situation, a process that's going to have different possible outcomes. You don't know what the outcome will be ahead of time, but you can measure it after it occurs. So an example of an experiment might be taking a six-sided die and rolling it. Doing that one time would be an experiment, and then you can record the result. I rolled a 4. Okay. So you have a sample point or an outcome. That's one specific result. So as I mentioned, you could roll a die and get a 4. You would then have a sample space. The sample space describes all the possible outcomes. So again, for a standard die, it's 1, 2, 3, 4, 5, 6. Those are the 6 possible outcomes. They're the numbers 1 through 6. And then you have an event, which is a specific collection of sample points or outcomes. So as we kind of mentioned here, we will define events as particular outcomes that we're interested in. So I may roll a die and get a 4, but the event I'm interested in for what I would call success would be if I were to roll a 2. Because like if I roll a 2, I'll maybe land on some square on the game board and I'll like win the game or something. So a sample point is just one outcome. The sample space is all the possible outcomes. And then an event is some outcomes. An event can be more than one. So like if I roll a 1 or a 2, that could be defined as an event. There's some examples here. Flipping a coin is an experiment. Rolling dice, rolling one or multiple dice, drawing cards from a deck, drawing multiple cards from a deck. It's also applicable to if you're doing surveys, if you're doing screening for diseases, which is a very topical example right now. Administering treatment to people who you think might be infected. That would also be an experiment. So determine the sample spaces for these experiments. How many possible outcomes are there? So flipping a fair coin 3 times. So if I'm going to flip a coin 3 times, what are the possible outcomes? Well, I could have a head, a head, and a head from my 3 coin flips. I could have a head, and a tail, I could have a head, a tail, and a head. I could have a tail, a head, and a head. I could then have a head, tail, tail. I could have a tail, head, tail. I could have a tail, tail, head. Or I could have tail, tail, tail. So those would be all the possible outcomes of rolling doing three coin flips. Rolling a single six-sided die, what are the possible outcomes? 1, 2, 3, 4, 5, 6. And these would be the sample spaces for these experiments. So, some rules for finding probabilities. Each outcome or sample point has its own probability. The probability of some event, the way we write that down is P of E. So P stands for probability. And then inside the parentheses, we put the event E that we are interested in. If there are n sample points, then the probability, as we mentioned, is between 0 and 1. And if you add up what this means, this is kind of a formula that may look like a bunch of gobbledygook to you. This just means take all the probabilities. The sigma means to add them all together. And that just means all the probabilities added up should give you a total of 1. If there are n sample points in the sample space and they're all equally likely, the probability of any of them occurring is 1 over n. So for instance, rolling dice, there are 6 outcomes in the sample space. So the chances of rolling a 5 would be 1 out of 6. The probability of any particular event is the sum of all the sample points in that event. So if I want the probability of rolling a 1 or a 2, I would add the probability of 1 to the probability of adding 2. So here we have the sample space written out for us. It's the same as what we had before. We're flipping 3 coins. You could have 3 heads, 2 heads, either front, first and third, or both in the back. And you can have heads, 1 heads with the same thing, head in front, middle, and back, or you could have no heads at all. So what is the probability of getting exactly 2 heads? Well, if we look right here, there are 1, 2, 3 outcomes out of a total of 8. So that would mean that there are 3 ways out of 8. My mouse is misbehaving. 3 out of 8 ways to get exactly 2 heads. Emphasis on the exactly. We don't want more than 2. We don't want less than 2. We want 2 and only 2. What is the chances of getting at least 2 heads? Well, if you have at least 2, you would still have the 3 that I already included, plus the one that has all 3. So there are 4 possible outcomes out of 8. As I'm sure you're well aware, you can reduce that fraction by dividing the top and the bottom by 4, and that gives you the fraction 1 over 2. The chances of getting 3 heads, well, there's 1 way and 1 way only for that to happen out of 8 total. This mouse is driving me nuts. All right, there you go, 1 out of 8. And then the chances of getting no heads. Well, no heads is another way of saying all tails. So there's 1 way out of 8 to get no heads whatsoever. So those are some of the probabilities for this example. Here we've got 6-sided dice. We're rolling 2 of them together, and we're going to add the results together. The question is, how large is the sample space? Well, if you count up all the pairs of dice, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. There are 36. If you didn't have that picture there, and you could just count them, where that 36 is actually coming from is actually this. For die number 1, there are 6 possible outcomes. And for die number 2, there are 6 possible outcomes. And one of the things we're going to see later in more detail is that if you do the possible outcomes from the first part and multiply that by the possible outcomes for the second part, that gives you the total possible outcomes, which is where the 36 comes from. Now again, you even have a picture here for your reference. You could just count them up and be like, oh, there's 36. But it's probably faster to do this. But anyway. All right, so we've got 2 6-sided dice. The results are added together. Find the probability of the following events. Leave your answers as a fraction. All right, so the total is exactly 7. Let's look back at this, shall we? What are the possibilities of getting 7? Well, there's 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. If you add all of those pairs up, you will get 7, and what you will find is that this is 1, 2, 3, 4, 5, 6. There are 6 possibilities out of 36. So that is the probability for part A, 6 out of 36. For part B, they say, what is the probability that the total is exactly 10? And again, note the use of the word exactly. Let's go back to our reference, shall we? So we want probabilities that give us 10. Well, 5 and 5 gives us a 10. 6 and 4 gives us a 10. 4 and 6 gives us a 10. So there are 1, 2, 3 pairs of numbers that give us a total of 10. This is 3 out of 36. And I suppose for good measure, we should reduce these fractions. 6 out of 36 you can reduce and call that 1 over 6. 3 out of 36, you can divide those both by 3, and that's going to be 1 out of 12. The total is greater than 7. All right, let's go back to our chart here. So we want something greater than 7. That means 7 is not included. We want at least 8 and everything above it. There's actually kind of an interesting triangular pattern in this. So here's 8, 4 and 4, and then this diagonal gives you all the other 8s with the way this is written. And then this diagonal is going to give you 9s, 9, 9, 9, 9. This diagonal is 10s, 10, 10, 10. This diagonal is 11s, and then there's a 12 all by itself. So it's this sort of triangle down there. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 ways to do that. So this is 15 out of 36. You can divide both of these by 3. And if you do that, you will get the fraction 5/12. Next, they say the total is between 5 and 10, and they also say inclusive. So inclusive means we will include 5 itself, we will include 10 itself. In the last example, you may have noticed we didn't actually include the 7s because we wanted things that were bigger than 7, but we didn't want to include 7. Here, we're going to do 5, we're going to do 10, and we're going to do everything in between. So let's look at our chart yet again here. Where are the 5s? Well, there's 3 and 2, 2 and 3, 1 and 4, 4 and 1. Where are the 10s? 6 and 4, 5 and 5, 4 and 6. And then essentially it's going to be every diagonal between those two diagonal columns here. So how many is this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So that is 27 out of 36. And these can both be divided by 9, which would give you 3 out of 4. Fun fact, another way to find that out, since there are 36 total, if you count the ones that would be excluded and then just subtract those from 36, that would be another way to figure this out. And we'll get into that concept in more detail later. That's called finding the complement. Here you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you do 36 minus 9, that will also give you 27, which might be slightly faster than counting all the way to 27. But there you go. Okay, here's another one. We've got a poll of some voters. We've got 260 people. And we asked them about their political affiliations. So we've got them broken down by male and female. We've got them broken up as either Democrats, Republicans, or independents. So the first thing that we're going to do is find the total of each of these columns. So let's add these up first. So what do we have? We have 42 plus 61 for the Democrats. And that will give us a grand total of 103. For the Republicans, we've got 56 plus 51. If you add that up, you will get 107. Here you've got 20 and 30, which is a grand total of 50. Going across the other way, for the males, you've got 42 plus 56 plus 20. That'll be a grand total of 118. This mouse is driving me nuts. 118, there we go. And then for the females, we've got 61 plus 51 plus 30, which is 142. And if you add the totals, that should give you 260, which is what they told us. And sure enough, if you add those up, you do indeed get 260. That's a good sign. All right, so let's read what the scenarios are saying. Assume a person is selected at random. Calculate the probability that the selected person satisfies the following criteria and round to 2 decimal places. So what is the probability the person is male? Well, the grand total for male is 118, and that's going to be out of 260. So what we're going to do is 118 and divide that by 260. If we grab a calculator and divide 118 divided by 260, I'll do that real quick here. That is 0.45. They asked for 2 decimal places, so 0.45. All right. What's the next one? The probability someone's female. Well, let's look at the total for the female, shall we? There are 142 of them. And so that's out of 260. 142 females out of 260. We're going to divide the top by the bottom. 142 divided by 260 is 0.55 if you round it off. It's 0.546. So if you round that off, that is going to be 0.55. All right, so that is the probability of picking a female. All right, what is the probability of picking a Democrat? Well, let's look at the total number for the Democrats, shall we? So for the Democrats, you've got 103 right there. Again, this is out of a total of 260. So the probability of choosing a Democrat is 103 out of 260. Let's find out what that is. 103 divided by 260 is 0.40 if you round it off. It's 0.396, so that'll round up to 0.40. That'll be another way of saying 40%. All right, Republicans. So if we look at the total for Republicans, there are 107 of them. So 107 divided by 260. This mouse is driving me crazy. 260. Let's see if we can make that look a little bit more zero-ish, shall we? So 0, there we go. All right, 107 divided by 260. What is that? 107 divided by 260 is 0.41. So the two parties are kind of neck and neck with each other. You've got 40 versus 41, a 40-41 split. All right, and then we got the independents. So the independents, the grand total are 50 of them. So as before, we're going to do 50 and divide that by the grand total, which is 260. If you do 50 divided by 260, you obtain 0.19. If you round it off to 2 decimal places. And so there you have it. That is that set of examples. All right, here we got the table filled in for us already. That's convenient. All right, let's keep on going here. So what are the chances that someone is a female and that they are an independent? So let's look at this table in more detail here. So the females who are independent, I've known quite a few independent females, I dare say, but what is that? That's going to be 30. This is the part where you've got someone who is female and independent. So this is going to be 30 out of 260 people total. Let's divide this, shall we? So 30 divided by 260 is 0.12. It's 0.115. Round that off to 0.12. So about 12% of the population are independent females. Next, what are the chances of having someone who is a Republican or a Democrat? So all of the Democrats are 103, and all of the Republicans are 107. If you were to add those up, that would give you a grand total of 210. That's from 103 plus 107. Then you're going to divide that out of the grand total, which is 260. Let's see what 210 divided by 260 is. That is 0.81 if you round it off. It's about 0.807, so if you round that off, that is 0.81. The chances of someone who is a female or a Democrat. All right, let's take a look at this here. So the females, you've got this, this, and this. And for the Democrats, you've got that and that. Now, what you might notice, 61 here is going to get counted twice if you just go by rows and columns. It is not fair to double count the female Democrats here. You only want to count the 4 individual totals that we have in this table. So what we're going to have to do is we're going to have to add up these individual values here. So we're going to do 42 plus 61 plus 51 plus 30. So we've got the two values for the Democrats. We've got two additional values that are only females. If we add that up, let's see what we get. 42 plus 61 plus 51 plus 30, and that is 184. And again, this is out of 260. So if we do 184 divided by 260, we will obtain 0.71. 0.707 rounds off to 0.71. What are the chances of getting someone who is male and not a Democrat? All right, well, so the males who are not Democrats, here's all the males right here. We're going to not include those 42, but we are going to include these two right here, because those are males who are not Democrats. That would be a total of 76. So what we're going to do is do 76 out of 260. 76 divided by 260 is 0.29. So that is the amount of voters, or the proportion of voters who are males and not Democrats. So that is that example. So that's just an introduction. We'll get into probability in greater detail with even more probability rules and probability tricks in our next section.